Hello, my name is Giorgio Morales, and I will be presenting our paper, Counterfactual Explanations of Neural Network-Generated Response Curves. To begin with, we will be talking about response curves, which are tools that allow analyzing the responsivity of a system to a particular stimulus that we call active feature. Here we have an example where the active feature is called x1 and the response variable of the system is y. The response curve consists of all response values taken by the system when using all admissible values of the active feature. Response curves are very important in some applications, such as in agriculture, where farmers are interested in the generation of N response curves, where N is the active feature and it represents the nitrogen fertilizer rate applied. In pharmacology, it's common to generate drugs dose response curves because they reflect the strength of a drug. Now, it's important to highlight that in the analysis of response curves, we focus more on the shape of the curves rather than in their values, because that's what describes the responsivity of the system to the variation of the active feature. So in this example, we could argue that these two curves show the same responsivity because they have the same shape. For our problem statement, we observe that in addition to the active feature, the response values may depend on other stimuli that we are going to call passive features. The problem is that in traditional approaches that are used for the analysis of response curves, they assume that the shape of a response curve is dependent only on the active feature. Now, that requires the strong assumption that the explanatory features are mutually independent, which is not always the case. So in this work, we will build on the statement that the shape of response curves may also be dependent on the interaction of the active feature with the passive features. For example, in agricultural applications, the end response functional form varies across the field given the variability of soil composition and other terrain characteristics. So we want to understand that variability. The contributions of this work are as follows. First, we present a method that generates aligned approximate response curves using neural networks. Here we have an example, and we generate an approximate response curve by varying the values of the active feature, which is the first one. For each case, we feed a combination of features into the neural network to obtain an estimated response value. Then we present a counterfactual explanation method that is posed as a multi-objective optimization problem. So here we have another example. The objective is to use an evolutionary approach that is going to generate a counterfactual sample that finds the minimum set of passive features that need to be modified so that the shape of the response curves generated for this sample shows a significant change in responsivity with respect to the original curve. We also present distinct local and global explanations that assess the relevance of individual features and combinations of features. So now let's talk about the method. We have a system whose response is denoted as y, and it is sensitive to n stimuli x. The relationship between them is given by this equation, where f is the underlying function of the system and epsilon is a random error. We suppose that the s feature is selected as the active feature, which means that the remaining variables represent the set of passive features p. Then the response curve generated for the selected active feature consists of the sequence of response values obtained by modifying the value of the active feature from its minimum to its maximum admissible value. The problem is that generally in practice, we don't know the function f, so we need to estimate it. We will do that by using a dataset X that consists of n samples and its corresponding set of target observations is y. Here, each sample is denoted as x sub j. Now we train a neural network f hat that captures the association between x and y. So the estimated response for the jth sample is given by this expression. We can use the network to generate an approximate response curve in a similar way to what we show in the previous slide, but using f hat instead of the function f. We said before that we are interested in the shape of the curves rather than in their absolute values. So we need to get rid of any vertical shifts. And we do that by using this alignment process that subtracts the minimum value from each response curve, as we see in this example. Once that the curves are aligned, the comparison of their shape is easier. The next step is to create the set RS that consists of the aligned approximate response curves corresponding to all samples in the dataset. This can be interpreted as a set of functional data. The objective now is to determine a distance metric that conveys the difference in shape between two functional data samples. By using functional principal component analysis, each curve can be approximated as an expansion of k functional principal components, as shown in this expression for sample xj, where v sub k is the value of the kth functional principal component, and chi sub k is the kth orthonormal function. The idea is that a functional principal component represents a distinct curve pattern, which means that curves with different shapes will be encoded with different principal component values. In this work, we used 3 components because they were sufficient to explain at least 99.5% of the variance of the datasets that we used in our experiments. Therefore, the distance metric that we proposed, d sub s between samples xj and xq, is the Euclidean distance of the transform curves in the transform space. Now let's talk about counterfactual explanations for response curves. Given a sample xj, x prime j denotes a counterfactual explanation so that its corresponding aligned approximate response curve has a different shape from that generated for the original sample, meaning that it shows a different responsivity. Note that we consider that two curves have different shape if their distance d sub s is greater than a threshold epsilon, which is a hyperparameter. The objective now is to find a minimum set of passive features that should be modified so that the distance between x and x prime is greater than epsilon. This can be cast as a multi-objective optimization problem that minimizes 3 functions. So function g1 maximizes the distance between the transform curves, but its value is truncated when the distance is greater than epsilon. G2 minimizes the number of features that are modified, and this is calculated using the L0 norm between x and x prime. G3 minimizes the distance between x and x prime by using the Gower distance, because it's possible that we have to deal with continuous, discrete, and categorical variables at the same time. Then we use the non-dominated sorting genetic algorithm 2, or NSGA2, to solve the optimization problem. The remaining question is how to select the best solution from the Pareto set. To do that, we select the solutions with the lowest G1 value, from which we select the solution with the lowest G2 value. According to this, we could have optimized G1 and G2 only, or G1 and G3 only. But in practice, we notice substantially faster convergence rates by optimizing the 3 functions simultaneously, which means that they were shown to guide the search more effectively. The final aspect of our method is to provide local and global explanations. A local explanation conveys which passive features have the greatest impact on the responsivity of a given sample, while a global explanation indicates which passive features have the greatest impact on the responsivity of a system in general. For a given sample xj, a local explanation is denoted as alpha sub j, and it represents the set of features that were modified when generating the counterfactual sample x prime. The global explanation is twofold. First, we calculate the individual feature relevance, which is the ratio of times that a feature was modified during the counterfactual explanation generation process of all samples in the dataset. We also report the 5 most repeated feature combinations, and by doing so, we identify which features react together and which feature combinations are the most effective. Now let's talk about experiments. For all experiments, we used a 10-fold cross-validation design. Something that is different is that for each iteration of the cross-validation process, the trained neural network was used to generate the response curves and counterfactual explanations for all samples in the dataset, including those from the training set. Now, this doesn't lead to biased results because when we generate a response curve, we synthesize samples that were not previously observed. So for our first experiment, we generated a synthetic dataset that consists of 10,000 samples that follow this equation. This simply represents the sigmoid operation, and we have 5 variables that are sampled from these distributions. The first feature is selected as the active feature, and we used a feed-forward neural network with 2 hidden layers, each with 100 nodes. For the NSGA2 process, we used 50 individuals with 100 iterations, and we also consider 3 different values for the hyperparameter epsilon. Here we have an example of the counterfactual response curves generated for a given sample. These are the original values of the passive features, and these are the generated counterfactual samples. What we observed is that the only variables that needed to be modified were x2 and x3, so that the response curves of the counterfactual samples have a significant different shape from the original curve, which is this one that is at the bottom. The previous process is repeated for all the samples in the dataset to obtain global explanations. This figure shows the individual feature relevance achieved for all cross-validation iterations and for all epsilon values. If we analyze the equation and modify each variable by the same amount, we'll find out that this is the feature relevance order or ranking. From the figure, we conclude that the results obtained by our method coincide with those obtained by the analysis of the equation that was used to generate the dataset. Notice that the relevance ranking of features is the same no matter what epsilon value was used. This is meaningful because it suggests that the selection of epsilon is not crucial when analyzing the ranking of variables. In addition to that, the resulting relevance scores were similar for all validation iterations, and this indicates that the neural network model learns similar functions across different iterations. Finally, this table shows that the most effective feature combination is x2 and x3, followed by x3 and x4 for the 3 cases. For our second experiment, we used real-world data, specifically 2 early yield prediction data sets of winter wheat. These are the inputs. The first one is the nitrogen rate applied, which is selected as the active feature. We have 3 variables that explain the characteristics of the terrain. We also have precipitation of the prior year, and we include backscattering coefficients that are obtained from radar images. This is a 2-dimensional regression problem because the inputs are 2-dimensional. They are patches of 5 by 5 pixels, and the output has the same shape. So instead of using a feed-forward neural network, we used a convolutional neural network that is specifically designed for yield prediction, and is called Hyper-3DNet-REG. Presented it in a previous research. This is an example of the counterfactual end response curves generated for a sample of the first dataset that is called Field A. These are the original patches of the passive features, and these are the counterfactual samples that were generated. We learned that the only variable that needed to be modified was VH, so that the shape of the resulting response curves have or show different responsivity with respect to the original curve. Similar to what we did in the previous experiment, here we have the global individual feature relevance values for field A, from which we learned that the topographic aspect is the most relevant variable. This is explained by the fact that this field is located on a steep, abrupt terrain. Regions that are facing north and east have limited sunlight and are more prone to snow retention, which may affect the responsiveness of the fertilizer. From here, we also learned that the most useful combination is the aspect with the VV variable in the 3 cases. In contrast, the experiment for field B showed that the most important variable is topographic position index, TPI, which is related to the ruggedness of the terrain, followed by the terrain slope. The difference is that field B is located on an almost flat terrain, and the most important factors are the variables that influence fertilizer runoff, which are TPI and slope. Finally, note that precipitation is assigned low relevance values in both cases, which may seem counterintuitive, but is actually suggesting that P is independent of the other features and does not affect the shape of the end response curves. In conclusion, we believe that quantifying the responsivity impact of all variables may improve the analysis of response curves. That's why we presented a method that estimates the impact that a set of passive features have on the shape of the response curves by generating counterfactual explanations. Results on a synthetic dataset coincide with expectation following the analysis of the equation that was used to generate the dataset. Then experiments on 2 crop yield prediction datasets confirmed that the models are reflecting what science would expect in crop production. In the future, we plan to use equation discovery approaches that approximate parametric equations in science applications, such as crop production again, and wildfire management. Thank you.